Welcome back, guys. In this video we start learning Smali, and we do this step by step, and we start with a really important component, maybe the most important component, and yeah, if we have understand this one, then the rest will be also not that hard anymore. Alright? Okay, let's go. Let's have a look at registers in Smali. So I pulled out my graphic tablet and we make some fancy drawings to explain this. Alright, before we dive too deep into this register topic, let's first have a look at a very basic function. Based on this, we analyze how the CPU is handling those single instructions, and then we will figure out how registers work in Smali. Alrighty? Okay. And so let's say we've got the following function. We've got public, a function that returns an integer value. This function takes two parameters and add them together. So we name this add power. And here we have our two parameters, int a and int b. And this function also has a local variable named sum. And this one is being initialized with 0. Then we have the sum, which is equals, now these two parameters gets added together and stored in sum. So, the sum is equals a plus b, and afterwards we return this variable, or this value in this variable, via return sum. Alrighty. This is a very basic function written in a high-level program language, but the CPU cannot handle it in this way. So therefore, this function is being compiled, and the compiler translates this high-level function into single instructions which can be handled by the CPU. So let's have a look into this, but don't worry, only on a very high level. Therefore, let's draw this line over here. Alright. So here now we have our CPU. This is our CPU. And this one has, of course, also some pins. Some of them seem to be not connected, and some of them, they could be shorted out. But yeah, this doesn't matter because we don't use them. Alrighty. So the CPU doesn't understand things like int a or int b, or also doesn't understand a variable named sum. What the CPU understands are registers. So a CPU has a register. And this one, for example, or this one, or maybe also this one here. And these registers are now some kind of placeholders for these values or these variables. In this case, for example, this register can hold the variable a, and this one holds the variable b, and this one holds the variable sum. If you're talking about smartphones, we are most likely having an ARM architecture. And an ARM architecture has registers named from R0 to R1, R2, R3, and also some other registers like the program counter, for example. Alright, now if we compile this code over here, then the compiler is translating these into single instructions, and this will end up in the following. For example, if we call this function over here, the first argument, this parameter 1, this one will be stored in our register R0. So R0 is now holding A. B will be stored into R1. And regarding to the other parameters or registers, we do not have any other parameter. Therefore, these registers are not being used in our calling convention over here. The program counter holds the value or the address of the next instruction, but for now let's ignore this. So this is simply just set to the next instruction, which is going to be executed by the CPU. Alright. The sum will be afterwards also stored in a register, and on the ARM architecture, the return value of a function will be stored in R0. So afterwards, R0 is not holding A anymore, it's holding the return value, which is sum. This is how a CPU is handling these values or references. I mean, it's a little bit more complex, but on a high level, it looks exactly this way. Alright, but what if we run out of registers? For example, on the ARM architecture, R0 up to R3 are being used as parameters. So these registers hold the parameters of a function. But what if our function now has 10 parameters? Then the CPU is storing the first 4 parameters in those registers over here, R0, 1, 2, and 3, and the others are being pushed onto the stack. The stack is the program memory, so this one over here. This one is the stack, and this is then holding the other parameters. So they get pushed into the memory. That's the memory. You might ask yourself why I'm telling you all of this. And to be honest, I've got absolutely no clue. Just kidding. Smali is acting on the same behavior. So Smali is also using registers to store their values or variables. It's pretty identical to the CPU. But of course, Smali has other registers. Otherwise, it would be absolutely ridiculous if Smali would also use these registers over here. That's of course not the case. So Smali has their own registers. And what type of registers? Well, let's have a look. Let's make a cut over here. So this is our Smali corner. There we go. The output in Smali depends on the tool we are using. For example, the JDX decompiler will summarize all these registers into one blob. The APK tool instead is splitting them up, and that's why I really like to use the APK tool. The APK tool splits them up into 2 parts. The first part is local registers. These are the local registers used in a function. For example, this one over here. In our case, we have int sum. This is a local register. Local registers only affects this function itself. So only registers which are being initialized or used in this function over here. The other type, do you have a guess what it could be? I'm pretty sure you do. The other type are parameters. And I mean parameters, yeah, that's not that hard. Parameters are simply just registers or values passed to a function. This one and this one, for example. Alrighty, in Smali, if we are decompiling an application with the APK tool, these parameters are named from P0 up to P something. P0 is also a special case. So P0 is most of the time the this operator. So that's a really special register over here. Therefore, those parameters normally start at P1 and simply count upwards. So this one would be P2. Local registers, they are named with V. So in local registers, we have V0 and it simply counts upwards. In our case, we have a local register or a local variable named sum, and this one would be our V0 register. But registers are not only regarding to local variables, like in this case, for example, V0, which is referenced as sum. For example, this value over here, this value 0. A CPU cannot handle 3 tasks at once. A CPU will split up this instruction over here in several different instructions, and therefore the value 0 will be also stored in a register. This can be V0. But it could be also another one, for example V1. And this is not a local variable, this is a local value which is temporarily stored in a register. So to make this a little bit easier, registers are just some kind of placeholders for values. Alrighty, one important thing we need to remember if we are working with those registers is that those registers, if we initialize them at the beginning, it doesn't have to be the same at the end. Not just regarding to the values, also regarding to the variables. For example, if we extend this function over here. So at the beginning, we are initializing V0 with the variable sum. And then let's say we have some bunch of other variables. V1 is holding D, V2 is holding I, and so on. Afterwards, we are returning, for example, V1. return, there's some letters missing, I guess. Yeah, there we go. All right, so the compiler is now generating this code, and in a certain level, for example, in between here, the compiler might recognize I'm not using the variable sum anymore. This one is not going to be referenced or returned from this function anymore. Therefore, we can recycle this register, because also those registers are very valuable for the whole program flow. For example, regarding to runtime performance or memory usage or whatever else. The compiler tries its best to optimize this code as good as possible. And therefore, if the compiler recognizes, oh, okay, the variable sum is not going to be used anymore, then it recycles the register which is holding this variable. In this case, v0 might be recycled, and it might be initialized with a completely different variable at the end. For example, set. And now let's assume the program is not returning v1, it's returning v0 at the end. If we take a look at the beginning of this function, then we might think, oh, okay, this function returns the variable sum, but this register has been recycled, therefore overwritten at this point, and yeah, the program returns this variable set instead. So this is something we need to keep in mind. Therefore, my approach is to keep track of every register, and you will see this during this course. So I write every Smiley line into some pseudocode line, what it does and what actual register is holding which value. By doing this, we can keep track of these registers and we do not lose control or get overwhelmed by all this stuff. In my opinion, this is the best way to learn Smiley, because if we have analyzed the program code, for example, this part over here, this program code, then we have reversed every single line which is in the Smiley code over here. And we do this during this course, and you will see, at the beginning it might be a little bit hard, but if you keep practicing this over and over again together with me, then you will be able after this chapter to reverse and also write your own Smiley code, which is super amazing. I promise this to you. If you keep on working together with me during the Smiley chapter and reverse and perform all these exercises together with me, then you will be able to read every single Smiley line, and you will be also able to write your own Smiley code. So you can patch an application in whatever way you like. Alrighty, so let's summarize this here real quick. I mean, we're at the beginning. So what is the key takeaway of here? Okay, so Smiley acts on registers, and if we are using the APK tool to decompile our application, the Smiley files or the registers are being split into two parts. One is regarding to local registers, and one is regarding to parameters. So local registers starts with V and parameters starts with P. Our parameters normally starts with P1 and simply upwards, P2 and so on. We've got a special parameter register which is P0. Let's write it over here. P0 is the this object most of the time. So in 99% P0 is holding this object. So for example, if you're writing Java code, we've gotten this dot. This is exactly the P0 register. Don't worry too much about this right now, we will learn this later on. Alright, what we also need to remember is, if we are initializing or assigning a variable or a value to a register, this register can be recycled. So if this happens at the beginning, it doesn't mean that this register is holding this variable or this value at the end of this function. So it can be overwritten, but it can be also completely recycled. So instead of having the sum variable, there could be a completely different one in there. For example, the set variable. We need to keep track of this, and you will learn during this course how we can do this. That's easy. We simply reverse engineer every single line of Smiley and we write down what this instruction does. And then we do not lose the track about this. Maybe one last thing I need to mention over here. So in my opinion, the best way to learn Smiley is having an approach on our graphic tablet over here, but then also some learning experience on the slides. So we take this code, we modify it a little bit, and then we will go through this once again on the slides. So it might be sometimes a little bit frustrating if we go through a topic twice on the graphic tablet and also on the slides. But for me personal, and also the feedback I received, this approach is the best way to learn Smiley, because Smiley, it's all about practicing and repeating what we have learned and applying it to new functions. So by having this, it's sometimes a little bit boring if we discuss this twice on the graphic tablet over here and also on the slides. But you will see the progress on yourself if we do this and keep doing it. Okay. So sometimes it's also a little bit better to have it on the slides instead of some messy arrowing going around over here. Alrighty, and let's write this code, decompile it, and then analyze the smiley part in there. Afterwards, we apply some patches and we will have a look at the modification on our slides. Therefore, let's switch back to the Ubuntu VM. Okay, here we are now at our Ubuntu VM. Let's write this function and have a look at a real-world application. So we're opening up Android Studio. Tools, Android Studio, bin, bash, studio sh. Okay, now let's go into this class and extend this method. So we go into player. And we add here a new method named public int add power, and we provide 2 integer values. And then we've got this sum, which gets initialized with 0. Then we have sum equals a plus b and return sum. Okay, let's compile this application and then we have a look into this with the APK tool, and we also compare this with the JDX GUI. So we go to build APK. We also do not need to call this method because it will be decompiled or it will be compiled into those smiley files afterwards in this player class. Sometimes there's some kind of decompiler optimization that strips out unused methods, but in our case we should be fine. Here we have our APK. And let's make this more clean. So we add a new directory within the apps. Smiley1 method register. Rename registers. Okay. APK tool d registers. Alrighty, registers, smiley, com, app hacking, smiley1, and here we have our player smiley class. Let's open this with Visual Studio Code. So I'm opening this directory over here. Then I go into this one. We close this one. Yeah, this is the old player smiley. Yes, so we close this one. And now we drag this new into this. Okay, and we have seen we've got this underneath here. This is our new method. Let's have a look into this. Therefore, we switch to the Java syntax first. Okay, let's have a look into this. We've got a method public named add power, and we do not know what this one is over here. This is just distraction for us right now. We will learn more about this later on in a separate section, but for now we do not care. Okay, next we've got this locals one, and this is the amazing thing of the APK tool. The APK tool is splitting up our registers into locals and parameters. So let's open the source code and keep it next to us and then do the comparison over there. Therefore, let me open this. There we go. Alright, so we've got our local register. A local register, in our case v0, we can find this name over here, here and here, can be some kind of placeholder, but it can be also a variable name within our Java code. So if we take a look into this, we can see we've got this int sum, a local variable over here. And this int sum is our local register, or is referenced by our local register v0. How do we know that this is the case? We can find this information here. It also starts with .local. So let's make this. From here over here. All right, we can see, let me clean those dots real quick. Okay, we can see we have our local register v0. And this one is now referenced by this label over here, sum. We do not care about this one. And now we know this local register v0 is a local variable in our Java source code in this function over here. And this variable is named sum. So sum is referenced by v0 as a local register. All right. So we know what this one means. Then we've got those two lines. We get rid of them. But here we can now see those parameters of this function. And we also got this labeling next to them. So this is the nice thing about the APK tool. We directly see, okay, we've got one local variable, in this case, variable because we've got this label over here, and we've got two parameters. So we can also find them over here, P1 and P2. The label regarding to the parameters are next to them, always. So we can find them directly here. Regarding to the local variable, we have to go into the source code and figure out if this is a local variable or simply just a placeholder. Then we've got this one here. So let's mark this real quick. Those are clear. Yes. Then we've got this one here, and this is super nice. This is really nice. We've got this line 9, and this line 9 means we can go into the original Java source code and check what is at line 9. And we can find this over here. There we go. So we do not know what this const / something means. We get rid of this. But this one is referring to the instruction that is in our line 9 in our Java code. So if we take a look into our Java code, we can directly see what's going on right here. We've got int sum is equal 0. And this is exactly what this line does. We know v0 is our sum. And we can also see this one here, 0x0 is the hex value for 0. So, and here by having this, we can look up simply the instruction and then figure out what this does. Or we can take a look at the original Java source code. But those line numbers do not always match. For example, in this case, if we open this application in JDX GUI, because we are hackers and we do not have the source code, we will have a different line number over there. Because the compiler has done some optimization and it's not storing this value in a separate variable, it's simply just returning this a plus b. And therefore those line numbers mismatch. But I would say regarding to real-world applications, those line numbers match at least for 90% of the time. So these are a really good indicator. They are not always correct or not always matching to the correct part, but most of the time they do. And if we get more and more practice within Smali, we directly see if those lines matches or if not. Okay, so we can most of the time rely on them. And this is super nice. Because putting them side by side, the JDX output, for example, or the dex2jar and the Smali code makes this whole reverse engineering process a lot easier. Okay, so we also know what this one means. Then we've got line 11. Let's have a look into line 11. We can also see we skipped line 10. Super nice. So it's always skipping those empty lines. It's like having assembly code with debug symbols. Even better in my opinion. So super nice. Okay, let's see line 11, this one over here. There we can see we are adding those two values, but okay, I mean we do not know what this one means. This instruction over here. We have talked about this one. So this is the reference to the local variable in our Java source code over here, this one. We can also write it the other way. v0 is referencing sum. I guess this is more accurate at this point. All right. So we do not know more about the add int instruction. I mean, okay, we can look this up and here we can see those two values gets added together, those two parameters, and then it's stored in sum. And that's of course what this instruction does. But we only want to focus on those registers. And this also helps us a lot because let's have a look into this. We can see we've got our v0 over here. Then we've got P1, oh, wrong color, P1, and we've got P2. So we now v0 is our sum, so we know sum. And we also know p1 is our label a, our variable named a. And a can be found here. The same for p2. p2 is b, p2. So we also got p2. And we do not know what this instruction does. But what we know is those three variables are involved in this instruction. And this is at least a super nice information, even if we cannot read the code on the left, isn't it? Unfortunately, there's a little bit of a downside to this, but this is not a real problem. We can handle this. If we reverse engineer an application later on, we need to keep track of this. In most cases, I guess in all cases, the parameter does not change. So p1 will be also or always referencing this variable. But our local registers might get recycled. So let's say we are using the sum variable here, then we've got a lot of code underneath this and the sum variable is not going to be used anymore. Then it can happen that the compiler is recycling this register v0 and adjust a new value to this. So at the beginning we figure out, okay, we've got our locals1. Locals1 is a real variable in our Java source code, and here we are returning this value. So we didn't talk about this one, but yeah, let's say we are doing something with this register right here. Then it can happen that this register is holding something different because it's not going to be used in the source code, and registers are sources that the compiler wants to optimize and reuse. And then the compiler says, for example, okay, I'm using the v0 register to store another value in there. For example, the value 10. And at the end, we think, okay, we are doing something with the variable named sum, but we are doing something with the value 10. And this is something we need to keep track on this. We do not know right now which instruction do change this register, so we cannot know this right now. We only also want to focus on those registers, and now I'm maybe a little bit too deep into this topic. But I would like to provide you as many information as possible at the beginning that you learn as much. Okay? I hope this is not too overwhelming right now. So if you reverse engineer an application later on, we simply need to keep track of those registers. We simply write this down in this way. It's not sum anymore, it's now, for example, number. And then we are good to go to move on in the source code. All right. So we also talked about this one. And last but not least, line 13, we also do the same. So I pick up my red color and then we take a look into line 13. We do not know what return really does, but I mean, okay, this is exactly the same like within our Java code. So return means we are returning from the function, and we are also returning the value stored in the register we are going to return. In our case, we are returning v0, and v0 is holding our sum. It did not change right now. This is a short function and the register has not been recycled yet. But if you have a larger function, please keep track on this. And that's all. We do not understand the Smali code, but if we look at the result right now, even by only knowing what registers are, we can figure out a little bit. This is a really good base we can work on. And from now on, we will learn more and more about Smali, opcodes and things like this. And within a few sections, you will be already set up to understand your first complete Smali program, which is super amazing. Okay, nice. Let's switch back to the slides and then we recap this once again. Because by repeating this over and over, you will learn this a lot more faster. Okay, so let's switch back. Okay, here we are back at the slides. Let's have a look into this. I did hide the Java source code. And let's talk about this one first. So take a look into the Smali code and ignore all the rest. Just focus on what we've learned onto this register topic. Can you find out how many parameters and local variables we have right now in this function? And maybe you can think about this, how it looks like in the Java source code. This might be a little bit too much expectation from me, so don't worry, this one is not required. But regarding to the amount of parameters and local variables, this would be super nice if you could find this out. You can pause this video right now and think about this, and in a few seconds I will move on this point. So let's have a look. Welcome back, and let's have a look into this together. So we've got this one over here, locals2. This means we've got two local variables, and we can also see those labels at the bottom. We've got a new label which is factor, and we've got our familiar label sum. So maybe we have now a new variable name in our Java code which is factor. This is just a well-educated guess, okay? Regarding to the parameters, let's have a look. We've got now p1, p2 and p3. It seems like I have added a new parameter over there. And the funny thing is, if we take a look into this line 2, those brackets, we can also see there has been an additional I in this bracket. And yeah, I guess we can resolve this right now and talk about this in the next section more in detail. This is the type of parameter we provide right here. And I means integer. So we provide here 3 integer values. Okay? But this is just a preview for the next section. So we didn't talk about this, and I didn't expect you to also identify this type right here. But it would be super nice if you have identified 2 local variables and 3 parameters. 3, this way, all right? Sorry for interrupting here shortly. So I don't want to confuse you, but I guess we should be pretty precise on this one. The line 3.locals2 means we are having 2 local registers, v0 and v1. And afterwards, these local registers being assigned to variables. This is in line 12 and also in line 20 the case. Therefore, we can afterwards talk about variables, but at the beginning, we only have 2 local registers. These local registers can be also placeholders, so they do not have to be assigned to local variables. Alright, I'm sorry for the interruption, but I guess this statement is very important in this context over here. Now let's move on. Okay, let's have a look into the Java source code. How does it look like? Yes, we've got 3 parameters now, and we've also got 2 local variables. One is factor and one is sum. Let's mark them here real quick. So we can see, okay, v0 and v1. These are now our local variable. And do not get distracted by all the stuff that's around our variables and registers over there. We will learn about this by making our way through this Mali chapter. Alright? Okay. So this is what I wanted to teach you in this section. We have learned something about registers. We know there are local registers and parameter registers. And we also know a register holds our value in case of a variable name or another value. For example, the value 0 can also be held by a register. Register can also change during the function. So if we initialize and register at the beginning, like here for example, we initialize v0 with 2, it doesn't mean that this register is still holding this value 2 at the end of this function. It might get reused, it might be overwritten, or there's some arithmetic operation happening on this register that changes this value. Alrighty. In the next section we take a look at the data types, and then we can understand half of the program already. Okay, so I'm looking forward to see you in the next section.